Hey everyone, this video is on word problems. This is the first day on word problems for exponential functions. And let's take a look at an example that we have here. So it says you've invested $700 that earns 9% interest compounded annually. Really quickly, please make sure that you have a calculator with you for this lesson because we're going to be doing a lot of calculations, and it's going to be important that you have it with you as we go through. So if you look right here, at year zero, your principal is how much money you have. It's $700. You've gotten zero interest because you haven't put anything in yet. You just started, and then that means your total amount is $700. Okay. So at year one, let's figure out how much money you have. Well, you have $700 to start off with, but to find the interest, you have to multiply that by 9%. So right here, this would be 700 times 9%, and this is how we would write 9%. So let's calculate what that would be. And you end up getting $63. So what's your total amount going to be? Well, it's going to be your 700 from your interest plus another 63. So this is $763. So then after year two, you're at $763. So what compound interest means is it's going to take the new amount and apply the interest on the new amount to find the next value, as opposed to applying the interest on the original $700. So here, that means we're going to do 763 times 0.09. So let's calculate that value. And we get $68.67. Which means that we now have $763 plus $68.67, which is $831.67. Well, and then I would take $831.67 and go from here. But this gets really redundant, unnecessarily redundant. So how can I do this a little bit faster? Well, if you look right here, this 700 that we have right here is 100% of the value. And then this 63 that we have right here is 9% of the value. And when you add those together, you get 109%. So all I have to do is just multiply 700 by 1.09, because that's how you write 109% as a decimal. Just like when it was 13% tax, you would multiply it by 1.13. So if I take 700, multiply it by 1.09, you end up getting 763, which is exactly what we had after year one. Now, after year one, multiply that by 1.09, you get $831.67. So now I'm going to multiply this by 1.09. And I get $906.52. Now, if you notice, it's 0.5203, but we'll round it to 52. However, to find the next value, we're going to want to multiply what we have here, the unrounded value, by 1.09 to get a more accurate answer. So I'm going to take that answer, multiply by 1.09, I get $988.11. And we're just going to keep going. So I'd like you to fill in how much it would be for year 5, 6, 7, and 8, and then come back and check and see if you agree. Okay, so these are the values you should have gotten for the last 4 years. And then the next step says to draw a sketch of what's happening. So let's go ahead and do that. So at year 0, you get $700. At year 1, you have $763. At year 2, you have $831.67. Keep going. So this is what it looks like. It's kind of hard to see what really is happening here. So we'll actually draw like a rough sketch of this instead after we take a look at what this is going to look like on Desmos. But before we do that, we have to develop some type of an equation. So if you notice, every single time after year 1, you've multiplied by 1.09 once. After year 2, you've multiplied by 1.09 twice. After year 3, you've multiplied by 1.09 1, 2, 3 times. Year 4, you've multiplied by 1.09 1, 2, 3, 4 times. So if you notice right here what's happening, if I were to write this out as an equation, if the total amount is y and the year is x, then what's really happening here is that you're starting off with $700 and you're multiplying it by 1.09 x number of years. So like, for example, here, after 8 years, I would be multiplying it by 1.09 to the power of 8. Let's try this. 700 times 1.09 to the power of 8. So you get this value, this $1,394.79. Well, I want to show you on Desmos what this really is going to look like. So if you take a look here, I have y equals 700 times 1.09 to the power of x. And this is what it looks like here. Like, it's starting at 700. And then if I were to zoom out on this, you can see here that this is definitely going to look like exponential growth, which makes sense because this is an exponential equation. Now, the growth isn't that fast because it's only 9% as opposed to like 20% or 100%. But regardless, it's still exponential growth. So we can say that it's going to look like this. So do you want to keep doing this to determine how much money you'll have after 10 years or after 30 years? What's a simpler way of doing this? Writing out an equation. Which in this example would be y equals 700 times 1.09 to the power of. All right, so now we're going to take a look at exponential growth and decay. Like, these are applications. And just a heads up that the general equation for exponential growth or decay is f of x is going to be equal to a times b to the power of x, okay? Where a is going to be your initial amount or your initial value. And then B is going to be your growth or decay rate. But to find B, you have to do 1 plus R, where R is the percent as a decimal. Okay, so let's take a look at an example here. So hoping to prevent extinction, we are told that we have 75 African bat-eared foxes. They were all moved to an animal reserve in Africa. The fox population increased by 15.8% each year over a 10-year period beginning in 2017. So it says to write an exponential growth function to model this relationship where P is the population and T is the time in years after 2017. Okay, cool. So generally we say f of x equals a times b to the power of x, but here we're going to use p instead of f of x and t instead of x, so it's going to be a times b to the power of t. Now, a right here is your initial value, so your initial value is 75, and then to find b, it's going to be equal to 1 plus r. Well, here, the r is equal to 15.8%, so we write this as a decimal as 0.158. So here, the b value is going to be equal to 1 plus 0.158. So b is 1.158. So putting that all together, putting all the information all together, we can now say p of t is equal to 75 is your a value, times your b value, which is 1.158, all raised to the power of t. So this is your exponential equation. Okay, then it says how many bat-eared foxes were present at the end of a 10-year period. So this is asking us to find P of 10. So to find P of 10, I'm just going to replace the T value, with 10. So when I plug that into my calculator, we should get approximately 75 times 1.158, all raised to the power of 10. We get approximately 325 foxes. Okay, so then you'd write your therefore statement, which I'm not going to have us do because of time in the video, but make sure you always add your therefore statement. Okay, in our next example, it says that a cattle farm has a population of 240 cows, but it's declining, that's really important, 3.4% each year. And then we're going to write an exponential decay function. So where P is the population and N is the number of years. So again, we always start with the general equation, which is f of t equals a times b to the power of t. But we're going to use P of n equals a times b to the power of n because it says to use P and n here. So now we know that A is still going to be that 240. It's still your initial amount. But this time B is equal to 1 plus R, just like we did before. But our R is going to be a negative 0.034 because it is declining. So B equals 1 minus 0.034. So B is equal to 0.966. So now I can fill in all that information here, and I can say that P of n is going to be equal to the A value, which is 240, times the B value, which is 0.966, and that's all going to be raised to the power of n. So this is our exponential equation right here. And then it says, what will be the expected cattle population after 5 years? So here we just need to find P of 5. So I'm going to do 240 times 0.966, all to the power of 5. And then here, I'm going to just type that into my calculator. So 240 times 0.966 to the power of 5, and we get approximately 202 cows. Okay. But again, you can get an accurate answer using logs, which we're going to learn throughout this unit. Okay, so a few more things to talk about. Half-lives. If we have half-lives right here, the general formula for half-life is going to be n equals n sub 0 times 1/2 to the power of t. Let's make this n of t, t over h, where h is your half-life. So how long it takes to cut in half. Okay, and then for doubling and tripling, it's the same idea. N of t equals n sub 0 times 2 to the power of t over d, where d is the doubling time. And then tripling would just be the same exact thing, except it would be a 3 instead. T over, let's say, P for triple time. Okay, I don't want to use T because T stands for time. I also don't want to use R because we used R for the rate. So I just don't want to confuse you with different variables. Okay, so how do we apply this? A bacterial culture began with 7,500 bacteria. So this right here is going to be your N sub 0. It's your starting amount. So actually, let's write this down, that N sub 0 is the original amount. And that's true for both half-lives and doubling time. Its growth can be modeled by using the function n of t equals 7,500 times 2 to the power of t over 36. So notice how right here, this has this 2 right here. So this means that it is doubling. But how often is it doubling? It's always doubling whatever that double time is right here. And if you look right here, That value here is 36, where t is in hours. So here, our doubling time is going to be 36 hours. So then how many bacteria are present after 36 hours? We have two choices. Our first choice is we could just do n of 36 equals 7,500 times 2 to the power of 36 over 36. But 36 over 36 is 1. So then 7,500 times 2 is 15,000. But if you really understand what's going on, all you have to do is know that after 36 hours, it will double once. So then your answer right here would be 7,500 times 2, which is 15,000. And again, write your therefore statement. Okay, and then the last question is, how long will it take for the bacteria to reach 3,200? So here, what we would do is we would say, well, n of t equals, we'll use the equation, 7,500 times 2 to the power of t over 36. And then I'm going to replace n of t with 3,200. And then I could use algebra to solve this, but eventually you're going to get a point where you have an exponent, a variable in the exponent, and you can only solve that algebraically with logarithms, which again, we haven't learned how to do. So our only option is to guess and check. I'm going to type in right here that we started with 7,500 times 2 to the power of, and then we'll start with 36 over 36 because we know that that will give us 15,000. That's obviously too small. So let's try another value right here. So let's try, 48. Still too small. So then let's try 72. It's still too small, but we're getting closer. So now let's try maybe 80. That is too large. So I know our answer is going to be somewhere between 72 and 80. So let's try 76. It's a little bit too high. So let's try 75. It's a little bit too low. Let's try 75.5. It's a little bit too high. 75.4, still too high. 0.3, too low. So we'll say 0.35. It's a little bit better. 0.355 is a little bit too high, so maybe 0.354, and we just keep guessing and checking and checking and checking until we get to the right answer. So we'll say it's approximately 75.35 hours. Okay, in our last example, it says radon has a half-life that can be modeled by this equation right here. So it's a half-life this time. It's modeled by this equation. We know it's a half-life because of this 1/2 right here, where t is measured in days. So it says from the equation, what's the half-life of radon? Well, in our equation, this number up here always tells us what our half-life is. So it takes 3.8 days to cut in half, okay? That's like what this equation is saying right here. Like regardless of what the original amount is, every 3.8 days, it's going to be cut in half. So if my original amount was 100, after 3.8 days, it's now going to be 50. If it's radon, okay? So it says how much of a 4 milligram sample is present after 11 days. So right here, we know that our M sub 0, our initial amount is going to be 4 milligrams. We also know that our time is 11. So here, what I'm going to do is I'm going to plug that information in. So I'm going to say M of 11 is going to equal my M sub 0, which is 4, times 1/2 to the power of 11 over my half-life, which is 3.8. That doesn't change. And then I just type that into my calculator and see what I get. So 4 times 1/2 to the power of 11 over 3.8. And my answer here is about 0.54 milligrams. And then don't forget to write your therefore statement. Okay? And then question C says, how long will it take a 400 milligram sample to decay to 25 milligrams? So let's fill in all of that information here. So we know that M of t is going to be equal to 400. No, sorry, is going to be equal to 25. That's the final amount. We know m sub 0 is 400, and we're trying to find out what the t is. So here I'm going to say 25 equals 400 times 1/2 to the power of t over 3.8. And then I'm just going to play around with some numbers until I get there. And then I actually want to solve this one algebraically, because this one turns out nicely in a way that I can actually solve it algebraically, and I'll show you how. So divide both sides by 400, and you get 1 over 16. And this is 1/2 to the power of t over 3.8. Well, 1 over 16 is the same thing as 1/2 to the power of 4. So here, now we can just set our exponents equal to each other. Multiply both sides by 3.8, and it would take 15.2 days. And don't forget your therefore statement. So that means right here that it would take 15.2 days. Let's double check to make sure this is right. So if it started off with 400, I'm going to multiply that by 1/2. Raise that to the power of 15.2 over 3.8, and you definitely get 25, and this one works. How did I know that I could solve this one algebraically? I just knew, I recognized these numbers right here, and I could see, oh, I had some foresight, and I could see that definitely is going to reduce nicely with a nice common base. Okay, and then this part right here, we're just gonna answer this question in class. So you don't have to do anything with this right now. Just save it for class, and let me know if you have any questions then as well. Have a good day.